But if you go out in the real world and work on some sort of data science or machine learning application, more and more those applications are being used in ways that impact people's lives. Right? For instance, think about how prediction may be used in college admissions. Right? 120,000 people apply to UCSD. Not all of their applications are read. Right? Somehow, someone needs to decide whose applications to read. Right? So that involves modeling. Right? Job applications. Right? You all apply to Google. Right? Somehow they're going to filter who to look at. Right? And, hopefully they look at all of you, but someone has to do this filtering. Right? Perhaps even more consequentially, criminal sentencing. Right? We're about to look at an example of an algorithm that predicts the likelihood that someone who has committed a crime will commit another crime. It's called recidivation. Okay? And that can have massive impacts on people's livelihoods. Right? An algorithm is predicting whether or not you should go to jail, essentially. Right? Or say, whether or not you should be approved for a credit card. Right? Algorithms are used to determine that. And if you're not approved for a credit card, then maybe you can't afford to pay for your medical bill or whatever. Right? Like, these models that we're building, for us, they seem like we're just running code in a Jupyter notebook, but think about how they can be used more broadly in a societal context. Okay? And so here's the first example I want to look at. The algorithm is called COMPASS. It has a very particular meaning, correctional offender management profiling for alternative sanctions. And it is this model, like I said, that tries to predict if someone who has committed a crime will commit another crime. Okay? And it's what's known as a black box model. And a black box model is one where you don't get to see how it is making predictions. Now, this is very different than, say, a decision tree or a linear regression model or even logistic regression. In all of those examples, you can look at the coefficients on different features, or you can look at how the decision tree is making its sort of classifications. A black box model is one where you just give it input, and it gives you back output, but it doesn't tell you what's happening under the hood, right? And so this group, known as ProPublica, did an analysis of the COMPASS algorithm, which is currently in use and was in use in several counties. And it found that it performed very differently for white Americans and African Americans. And in particular, we're looking at two different kinds of errors here. The first one is labeled high risk, but didn't reoffend. Okay, and what being labeled high risk is essentially the model saying, we think you are going to commit another crime. So it's predicting positive, but they actually didn't reoffend, so this is kind of like a false positive. Right? So think of the numbers in the first row as a false positive rate. Okay, and this is one of the other evaluation metrics in that big Wikipedia table, false positive rate. Here you can see the false positive rate for white Americans was significantly lower than it was for African Americans. Right, so there were way more false positives proportionally for African Americans. Okay? If we look at the second row, labeled lower risk, yet did reoffend, labeled lower risk, well, that's saying we don't think you're going to commit another crime, so the prediction is a negative, but they actually did reoffend, so that means your prediction was wrong. That makes it a false negative. The false negative rate was actually much higher for white Americans. Okay, so overall, it just seems to be predicting more commonly that white Americans will recidivate less frequently than African Americans. So do we see how this model is performing differently for different groups? Okay. And so this is an example of an unfair model where its performance is better on one group than it is on another group. Okay, so do we see the issue with this and how it can sort of impact real people's lives? Okay. There's a very informative article here. If you click this ProPublica link, you can read all about it. It's from 2016, I believe, but this is where all the charts are from. Okay, there's actually a testimony in there of a white American who served 5 years in jail and was surprised at his risk score being so low. He's like, I think I'm more dangerous than that. My score should have been higher. But it actually wasn't, right? Okay, here's another example of these sort of evaluation metrics applied to gender facial recognition algorithms by Facebook, Microsoft, and IBM. Now, I question why we even need a gender facial recognition algorithm in the first place, but I guess these companies have more money than good ideas, so they're doing stuff like this. But anyways, a paper, which is also linked in the lecture slides, looked at how well these gender facial recognition classifiers worked, both from all three of these companies, and they found that they work very differently on male faces and female faces, and also darker faces and lighter faces. Okay, and if you look at the error rates, which you can think of as being 1 minus the accuracy, the error rate is actually highest for females with darker skin. And it's actually the lowest for males with lighter skin. So LM means lighter skin male, DF means darker skin female. Okay, so this gender facial recognition classifier is working way better for certain groups than others. And so this is another example of unfairness. All right? And so you may wonder, like, okay, who cares what this classifier is saying? Well, think about all of the places where facial recognition algorithms are being used, right? Not necessarily gender facial recognition algorithms, but more generally, right? If, like, the next time you fly internationally, if you go to a global entry booth, if you just look at the booth, your name will pop up. That happened to me once, and I was like, this is crazy. Like, how did it know who I was, right? So they're watching us, right? And they're clearly not doing it so well, right? So this can, again, actually impact people's lives. So a question we may have then is, how does this bias occur? We kind of addressed this already. The bias is coming from the data sets that we are using to build these models, right? It's not because Microsoft or Facebook was like, let's intentionally make this model work worse on female individuals with darker skin. It's just that they weren't calibrating for sort of the appropriate diversity in their training sets. So in particular, what are some issues that could sort of arise in the training data sets? One, like I said, they might not be representative of the broader population, right? And if you don't have, say, enough examples of minority faces, your model just won't really know what to do with them, and so it'll perform worse on them. It may also be the case that the features that you are using to build your model really only tell you something meaningful for one group over another group, right? Or the training data may encode existing human biases. Again, not because, say, someone was like, I want this model to perform worse for certain people, but because of how the data is collected, right? The data didn't just spawn from somewhere, someone had to go collect it, right? And maybe for whatever reason, people wanted to collect, this kind of data because, they thought it was easier or whatever, right? So human biases will sort of, find their way into our training data and then find their way into our models, even if we are, say, not biased, right? So this is still something we need to look out for. So here's the final example I want to show you. English, as you know, is not a gendered language. So this is very different than, say, French. Okay, in French, every noun has an associated gender. So the word for dog, chien, that is a masculine noun. Okay, English doesn't work like that, right? The word scientist or teacher, those are not inherently gendered. With that said, humans subconsciously assign genders to different words, and different genders sort of occur more often with given words in texts, right? So you can try and infer what the most common gender associated with these different words are, right? Not because these words are inherently gendered, but because these are the sort of contexts in which these words appear, right? There is nothing inherently feminine or masculine about a soldier, right? But you can sort of infer what our model will think its gender is. And so how might that present itself practically? Well, let's compare English to a language that doesn't have any gender pronouns, right? So English is not gendered, but it has gender pronouns, for instance, he and she. Turkish doesn't have any gendered pronouns at all. So there's no he or she in Turkish, there's just the letter O. So that means both he and she. Does anyone speak Turkish here? I'm going this summer, so I should learn how to speak it, but I guess that's why we're going to use Google Translate. But anyways, so if we look at these sentences, what they are saying is they are blank, where blank is a different sort of profession, right? And so since they're Like we didn't say he is or he is or she is. These should all be gender neutral when translated back to English. But that's not what happens. So if we zoom out, this is how you say soldier in Turkish, and it says he is a soldier. This is how you say teacher in Turkish, and it comes back, she is a teacher. Okay, so it's sort of imposing existing biases in the English language, even in translate. Now this is improved over what it did before. So if you just put one at a time, it should, actually let's just do this. Like if you just put one at a time, it shows you both the feminine and masculine translations of a term. Okay, but when I put multiple terms in at once, I guess it just inferred what it thought it would be, right? But if this were perfect, it would just show us a gender-neutral singular they in all of these cases, but it's not doing that. Right? So it's imposing existing biases in the English language sort of into this model. Right? And why is this happening? Well, it may be because, say if we go back here, in the English language corpus that Google Translate is trained on, the English pronoun that teacher appears most commonly with is she over he. Right? Even though there's nothing inherently feminine or masculine about teacher. Yeah?